Okay, so now I'm going to complete this set of notes, and if you skip the previous part of the video, all I showed there was where I used some calculus to show where some of our numbers in the SAS output are going to come from. They come from maximizing the likelihood function. And now we're going to talk about likelihood ratio tests. So similar to the overall test and nested F test in multiple linear regression, we'll sometimes want to see if a reduced model appears to do as well as a full model. Okay. The partial F test, or the nested F test, we called this the nested F test, compared the sum of squares due to the error between the full and the reduced model, right? The likelihood ratio test is actually going to compare -2 times the log likelihood for the reduced model to -2 times the log likelihood for the full model. So it's the same idea. It's the same idea, but instead of using sums of squared errors, we're going to use something called the -2 times the log likelihood function. If you watch the previous video, you'll get an idea of where that -2 times the log likelihood function comes from, but it doesn't matter too much if you don't know that. What you have to know instead is here's the formula for the likelihood ratio test. This is the test statistic. The likelihood ratio test statistic is -2 times the log of the likelihood for the reduced model divided by the likelihood for the full model. Or, since we're taking the log of this ratio, we can also take -2 times the log likelihood for the reduced model minus the log likelihood for the full model. Okay, the log of a ratio is just the difference in logs, is where that comes from. So when the null hypothesis is true, and again, this all assumes that we have a large enough sample size, then this is going to follow a chi-squared distribution with the degrees of freedom equal to the difference in the number of parameters, just like the nested F test in multiple linear regression. Okay, so again, the degrees of freedom is going to be the difference in the number of parameters between the full and the reduced model. It follows a chi-squared distribution instead of an F distribution, and you might remember something about chi-squared distribution from Stats 212, but basically it looks a lot like an F distribution, but it only has 1 degree of freedom. We don't have to worry about the numerator and denominator degrees of freedom. It has 1 degree of freedom, and the degrees of freedom are the difference in the number of parameters between the full and reduced model. So if we compare a full logistic model with our Donner data, where we have age and sex as the explanatory variables, to a reduced model without either of these, so intercept only, what are the null and alternative hypotheses of interest? And again, I want to rate these out in terms of the betas, but the null hypothesis is that beta 1 equals beta 2 equals 0, and the alternative is that beta 1 is not equal to 0, or beta 2 is not equal to 0. Right? So let's do this. Okay, so again, here is, we're going to do the likelihood ratio test that I just talked about. Okay, so here's our parameter estimates, but now we're going to focus on this part of the output over here. Okay. So intercept only, we're going to compare 2 models here. Intercept only is a model that only has beta 0 in it. Intercepting covariates is going to be a model that has beta 0 plus beta 1 times age plus beta 2 times sex. Right? Again, in the parameter estimates, beta 0 or B0. This is beta 0 hat, or little b0, beta 1 hat, or little b1, and beta 2 hat, or little b2. I used both those notations. Sorry about that. Okay, but now over here we're talking about the population parameters, not the sample estimates. And what we're going to focus on is this line, -2 times the log likelihood. So my likelihood ratio statistic from the previous page, remember, the likelihood ratio statistic is -2 times the log likelihood for the reduced model minus the log likelihood for the full model. Okay. Here's -2 times the log likelihood for the reduced model, has the intercept only. The full model has the intercept and the other beta terms, right? I can get to the reduced model by setting these two terms to 0. So the likelihood ratio statistic is equal to -2 times the log likelihood for the reduced minus the log likelihood for the full. So in this case, -2, and we can multiply the -2 through, and the -2 is already multiplied in here. This is minus log likelihood for the reduced, -2 times log likelihood for the full. So this would be 61.827 minus 51.256, which is equal to 10.57. Well, where's that? That's where this test statistic for the likelihood ratio test comes from, for testing the global null hypothesis that all of the betas, all the non-intercept betas, is equal to 0. Okay. It has 2 degrees of freedom because there are 2 parameters being tested. What does a chi-squared distribution look like? It's also right skewed and positive. So a chi-squared distribution looks an awful lot like an F distribution. Right? It's positive. This is a chi-squared distribution with 2 degrees of freedom because there are 2 parameters being tested. My test statistic is 10.57. So the p-value lives out here. If I wanted to calculate that p-value, I could say data chi p-value equals 1 minus, there's a prob t, a prob f, there's also a prob chi. We're going to put, and the first argument for the prob chi function, just like for prob t and prob f, is our test statistic, 10.57. This is our chi-squared stat. That x, funny squiggly x symbol is a chi. So this is a chi-squared stat that we got up above. The second argument, what do you think that is? Degrees of freedom. Proc print, and run that. And if you do that, as a matter of fact, let's do that. Why not? Okay, go back to SAS here. I'll say data chi p-value equals 1 minus prob chi. Again, we use 1 minus because we're always interested, the p-value always lives to the right in these right skewed distributions. And so we have to take 1 minus because the functions calculate the area to the left. So this should give us our p-value. .0051, I'm going to say. Don't round it. 0.0051. So this area is 0.0051. Well, where is that? Right. This is the same as our p-value up in the table. Okay. So we get a small p-value. So we can summarize this. Let me just also say here, one thing I forgot to say, just to make very clear, is that the degrees of freedom is the number of slopes in the full model minus the number of slopes in the reduced model the number of slopes in the full model, we have age and sex, so there's 2. Number of slopes in the reduced model, it's intercept only, so there's 0. So that's where the 2 is coming from. So after all this, we can say we have sufficient evidence that age, I'm going to say and or sex. This test doesn't tell us which one, it just tells us at least one of them is useful for predicting survival. I'm going to say for predicting survival probability. In, not always, but in a situation like the one the Donner Party was in. Hopefully we won't see a situation like that. But that's how we calculate the likelihood, the overall global likelihood ratio test statistic for testing whether any of our betas are useful in the model. Now let's take this a step further. Suppose now we want to consider a larger model. Let's throw in some age squared, an interaction term, age by sex, and let's also throw in age squared by sex. Why not? Okay, we only have 45 observations, but let's go ahead and throw all these terms in the model. And note that when I write this, so model, I'm again modeling event equals survived. When I write this, I can write that out just like procglm. I can put the age squared terms directly in the model. I don't have to define them ahead of time like I did for procreg. So this is my full model. And the model now has 5 slope terms, because I'm adding my higher order terms here, age squared, age by sex, and age squared by sex. Here are the model fit statistics. I didn't give you the likelihood ratio test, but because we're not going to test that just now, but if we want to compare this fuller model with these extra terms to the reduced model that only had age and sex in it, we can ask, are any of these higher order terms useful? So we can also use a likelihood ratio test to compare nested models. That's what it's always used for, but in this case the nested model might be this full model compared to the reduced model on the previous page. So the hypotheses that we might want to test, H null in this case, if we want to see if we can get rid of any of these higher order terms. If this is beta 1, beta 2, we might say beta 3 equals beta 4 equals 0, or equals beta 5 equals 0. Those are the betas attached to the higher order terms, h squared, h by 6, and h squared by 6. The alternative is at least one of these betas is not equal to 0, my shorthand term. We need a test statistic. My likelihood ratio test statistic is minus 2 times the log likelihood for the reduced model minus the log likelihood for the full model. My minus 2 times the log likelihood for the reduced model, I can look back at this previous page, and it's 51.256. This is the minus 2 times the log likelihood for the model that has the intercept and covariates for age and sex. So minus 51.256, or 51.256, sorry, minus, or negative 2 times the log likelihood for the full model. So minus, that would be 45.361 is the negative 2 log likelihood for the full model that has the intercept plus all these other terms in it. And if you calculate that out, it'd be 5.895. How many degrees of freedom do we have here? There were 5 parameters in the full model, so 5. There were 2 slope parameters in the reduced model, so it's 3. It's the same as the number of parameters being tested in our hypothesis here. Right? Degrees of freedom is 3. We can draw a picture. It's always a great idea to draw a picture of our chi-squared. Again, this is a chi-squared distribution. Chi-squared distribution with 3 degrees of freedom. Stick our test statistic on here, 5.895. P-value always lives off here to the right. Now we can use the function 1 minus prob chi 5.895 with 3 degrees of freedom. And I'm going to go to SAS quickly. I already have my code in here. So I'm actually just going to use the same code here and change this to 5.895 with 3 degrees of freedom. .1168, 0.1168. So this area that I just calculated is 0.1168. So now my conclusion, I'm just going to shorthand it here a little bit. I'm going to say insufficient evidence that the higher order terms are useful, which is actually good news to me, because the higher order terms, if we start throwing things like age squared, age by sex, and age squared by sex into the model, it gets, a little more complicated to interpret. But this test tells us we don't need any of those terms. We don't have any evidence that all of those terms are not equal to 0, so we can leave them out of the model. And I just have a note down here. If you remember, in a multiple linear regression test for testing individual terms, one term at a time, the f-test would be equivalent to the t-test. That's not the same in logistic regression. So that's how you do a likelihood ratio test. I just want to conclude. We're not going to go through any examples of this, but I want to conclude by saying that if you have a bunch of x variables and you want to figure out which one should go into your model, we can also use things like forwards, backwards, and stepwise selection methods. And it's very similar to proc reg, at the end of your model statement, you can use selection equals forward, selection equals backwards, and selection equals stepwise. So you can try this if you want to. We can also specify SLA, SL stay, and SL entry options for giving the significance level for coming into the model or for staying in the model. So here's an example of using stepwise selection. I'm not going to go through this because it's very much the same as we saw for multiple linear regression. We can also use the AIC or the BIC, and the BIC might be indicated as SBC, or as you saw, it actually Proclogistic for some reason abbreviates it as SC. Why they can't all be the same, I don't know. And it provides these criteria again in your model fit statistics. So smaller AICs are better, which indicates here the AIC in this full model that we just fit, the AIC would have selected the full model over an intercept-only model, whereas the Bayesian criterion would have selected an intercept model over using this full model. So you can use AIC and BIC as well to select models. There's nothing like a all possible regressions approach in logistic regression, so you really have to fit one model at a time and simply compare the AIC and the BIC, and the smaller value of either of these is better. And you can try out the selection option in SAS to see what that will do for you. And that's actually the end of these notes. So excellent.